Okay, recording.
Okay. Um, so today I'm going to be talking about, uh, we're going to be talking together about a puzzle from an event called the MIT Mystery Hunt. So the first thing, have any of you heard of puzzle hunts before?
New to me.
Also new to me.
Yeah, I think they're new to a lot of people. And I don't have the full history of everything called a puzzle hunt before, but the very brief history is probably something like MIT had something that was like a scavenger hunt, and they decided to make it more interesting by adding puzzles. And over the course of a few years, they inadvertently invented a new type of puzzle and new type of puzzle event that the collective term for is puzzle hunt. But every year on Martin Luther King Jr. weekend, the MIT holds an event known as the MIT Mystery Hunt, which is perhaps the most famous puzzle hunt. But now there are many puzzle hunts all around the world and some online, and many bars have a thing called the Puzzled Pint where they hold smaller versions of a similar type of event. Let me see, I had something else to say. Um, and yeah, and the other thing I want to emphasize is it's really a team thing. So you go to the mystery hunt or you go to the puzzled pint in a team of 4 or 10 or 50 or 200 or something like that. And you primarily solve puzzles together. And maybe there's some theming and some art and some story, or maybe there's not so much of that. Um, and generally, for the most part, the puzzles are a particular type of puzzle that's roughly unique to these puzzle hunt type events. A math person and puzzle solver named Mike Devlin, once famously said, "Imagine a word search. Now imagine you aren't told what words to look for. Now imagine you aren't told it's a word search. Now imagine it isn't a word search." Uh, that cryptic quote was intended to give an idea of what puzzle hunt puzzles can be like, but that's a little bit too cryptic. So, as a sort of amuse bouche, I'm going to go through and kind of spoil immediately a puzzle presented by someone who goes by Dr. Sudoku that just gives you a little bit of a taste of what you might expect before we dive into trying to solve a puzzle together. And by solve a puzzle together, I might speed things along. It's kind of like I've baked some things in the oven beforehand, and you can to help you pretend like you're on a larger team of people working on it. But I still hope that you'll all be able to contribute as we work on it. So here is a sort of tiny puzzle, I think by Dr. Sudoku, and it starts out with a word search, and I'm skipping to the part where the word search is already solved. So maybe you have this cryptic grid of letters, and they don't tell you it's a word search, but someone on your team recognizes the names of some famous artists. You got Raphael, you have Malevich, uh, uh, Delacroix, etc. And so they figure out, okay, it's like a word search. Let's find all those famous artist words, cross them off. Um, and you do that, and it's like, okay, I did it. What's the point? Well, if you look at the letters that are left over, UNUSEDARE, and then some more, it says unused are a Sudoku. And so unused sounds like a word. Sudoku is probably a word you know. So the unused parts of this word search are somehow a Sudoku? Well, this is an 11 by 11 grid, but there are words all on the outside, uh, or at least on the outside rim. So this is a 9 by 9 part that has some unused letters. And so if you just write that 9 by 9 part with the unused are a Sudoku blah 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 blah, then you get a 9 by 9 grid with some letters filled in. And if you think about this, you realize, oh wait, there's only 9 letters there. and I'm not even going to count through them, but there's 9. And so you could solve the rest of this word search as a Sudoku. And you do that, and now somehow, generally these puzzles in a puzzle hunt almost always have a answer that is a single word or short phrase. And so we have this solve Sudoku, and how are we going to get a single word or short phrase? Well, we read like the rows and they're kind of nonsense, and you read the columns and they're kind of nonsense. But one thing you could read is this diagonal, and it says run around. And that would be the answer if this were a puzzle in a puzzle hunt. So to recap, they would give you this sort of grid of letters, and you might not be sure if it's a word search, but maybe you'd figure it out, or someone on your team would recognize some of these names, and then you would solve the word search, and it would reveal another step, that it's actually a Sudoku to do now. Then you would do the Sudoku, but then you'd still need to figure out another step. How do I get a word out of this Sudoku? And then someone would think about the diagonal and figure out the answer. So that is a little taste of what a puzzle hunt puzzle is like, where they don't tell you what to do, or they don't often tell you what to do, or don't tell you every step of what to do, but somehow steps lead to more steps, lead to more steps until you end up with the answer. So I'm going to pause now in case anyone has any comments or questions about how that sort of little example works before we get into our real main event.
This looks fun. I'm looking forward to it.
Yeah. Great. So that was a puzzle, and if you all promise not to pull up this website yourself because it has a solution that will kind of ruin the fun of trying to solve it together, I can show you exactly what a real puzzle that we're about to work on from the 2022 MIT Mystery Hunt looked like. So it looked like this, and there was some theming to this part of the puzzle hunt, but the main point is just there's a title, which probably doesn't affect the solution, but it's just lists of large integers. And then the entire puzzle is this. So there is n equals this gigantic number, and the text, helpful, n is a product of two 140-digit primes. The factors of n, when read appropriately, will tell you the answer to the puzzle. And then factoring practice in a bunch of integers, some are bigger than others, and extra practice with some other really big numbers. Maybe almost as big as n, but maybe not quite. But I want to emphasize that the numbers of the size of this n and these extra practice numbers probably, well, like numbers at these sizes, typically you're not going to be able to factor them even if you, throw whatever complicated, crazy, modern factoring algorithms we have with modern computers. There's a comment of like, okay, time to break out the quantum computer to try and solve this because, you're not going to be able to factor this n with any current computers naively. We do not have the technology to do that. And yet, the puzzle says the factors will tell you the answer, and they tell you, don't worry, this isn't like a product of a bunch of small numbers that you'll be able to factor. It's a product of two gigantic 140-digit primes, and it does not tell us anything else. But more than that word search example, it at least tells us the goal in some sense. Okay, somehow we can get the answer if we can find the 240-digit primes that factor this n. Great. That doesn't give us much to go on, but we have this factoring practice. And so, since there's nothing else on the page here that's relevant, I'm going to switch to a little Google Sheets, which is just, and MIT Mystery Hunts these days usually provide like a copy to clipboard function to make this easy. So we stick it into Google Sheets just so we have all the numbers. And yeah, we're not going to be able to factor. You can't just throw in a random one of these large numbers into, Python or something and factor it. So we need to do something. What do you all want to do?
All right, well, I'll just start throwing out some random ideas, I guess. I mean, from the last factorization talk, we kind of, learned that there were different factorization methods which are better for different types of primes. I figure one thing that you could do to just start is begin with a naive approach. Like, for all we know, that number is um, I was going to say divisible by 3, but I guess it does say they're both 140 digit primes. So I guess starting off with dividing by 3 and checking if that works is not going to do much. Another thing I was thinking is maybe some of the same maybe there's a pattern to the factors of the primes and in the rest of the page, or maybe there is a pattern used to generate the large primes that are used to create them. So we could just go ahead and figure out what the factors of the bottom ones are, and then from there hopefully come up with some idea of what the type or what class the primes of the top number were selected from, and that could inform our approach.
Sure. Yeah, I like your thinking. And just to be clear, when you say the bottom ones, do you mean these big ones under extra practice, or these ones under factoring practice?
I just meant anything that wasn't the top, like the question itself.
Okay. Yeah, because these extra practice numbers are almost as big as the n at the top.
Okay.
And so, unless you kind of get lucky with your approach, let's pretend that like someone on our team tried asking some basic factoring algorithm to handle these extra practice numbers, and it couldn't touch them in a reasonable time frame.
Cool.
But
one other
these other numbers.
Are we
Oh, go on.
usually? I guess we're allowed to use Google in these problems. Can you of course bar Googling the actual question itself, but is that part of the puzzle? You're allowed to search things.
You're allowed to. I will say that for this particular puzzle, it's not going to help very much.
Okay.
Um,
I was just going to Google
or
140 digit primes and see if there were any common well-known 140 digit primes or something.
No. So yeah, you do that and it doesn't work.
Okay. Okay, cool. Okay.
But some of these factoring practice numbers
Uh-huh.
are small enough to factor.
Cool.
And looking at the normal practice numbers, a few of them have suspiciously large amount of repeating digits in a row.
I saw that too. There's one
That is true. That's a lot of sevens right there, and there's some nines here. That's an interesting observation. I'd say hold on to that. So one thing we could do is we could try to factor these factoring practice numbers. Yeah. Now, depending on you and the members of your team, maybe you have more or less experience with programming or more or less experience with factoring. So to simulate some sort of not knowing too much about factoring, but being able to load a package in some programming language, I asked Mathematica to use its default factoring method for up to 1 second on all of these numbers in factoring practice. That'll sort of simulate, what your team might figure out pretty quickly by throwing these factoring practice numbers into some program somewhere. So we do that. So in column A, these are just the factoring practice numbers, not those huge extra practice numbers. And it turns out all the ones that we can factor in a second with Mathematica, they are a product of exactly 2 primes. They're not like powers of primes, they're not like 3 primes or anything. They're all a product of 2 primes. And some of these that say 2 top are ones that would take Mathematica more than a second. And some of the very longest ones, you would probably need to be smarter. Like maybe this one you could do in a reasonable time, but maybe you need to look up some special factoring algorithm or something like that,
right?
Because it's so big. But we still have a lot of factors here, and we do have this pattern, and it looks like all the numbers probably are a product of 2 primes. I'm going to make this a little bigger. There we go.
They also appear to have repeating digits.
Yeah.
All the primes, or a lot of the primes.
So yeah, I guess just so shout out some What do you notice about some of these? Here's
I
a
think there was
sample.
one that was like 1 1 1 1 1 2 1 1 1 1 1 a little bit down. Like
Oh,
they have uh
let's
I think
see
it was
A
here.
lot of repeating digits.
yeah, there that
Oh,
one
like
right
this
there.
one.
Yeah.
This has a lot of ones, and then a two, and then a lot of ones.
Hmm.
I wonder if that massive prime is then a product of two rep units.
Two what's? Rep
The
units?
massive number
Well,
is
What is a rep unit?
a repeating unit, just a long
Oh,
string of
oh, okay,
ones.
gotcha. Um,
so it says 240 digit primes. So if 140 ones is prime, they can't both be rep units, but maybe it could be something like that.
Yeah.
Okay,
what
so
can't
we
both be
have
rep units?
uh,
I mean, if like
there would be the same number.
say that again. I don't follow. You're saying if the
If 240 digits are both made only of ones, then they're the same number. And
oh
then you
okay
wouldn't really
sure.
say it's a product of two primes.
Well, it could be a product of two. Oh, is rep unit just only ones as opposed to like three 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 three?
Yeah.
Sure. Okay. Gotcha. Um. Well, I'm trying to see. I mean, now I guess what I'm looking at is like, is there some pattern that we can deduce from the left number that would imply that it's like all ones on the right or all ones on the left? But I think the answer I'm coming to here is no.
Actually, I think it can't be because if the number of digits in a number is not prime, then the number like that can't be prime.
Oh, okay. Well, okay, so we have let's keep looking at these factors. So we have, this factor has a lot of ones and then a two.
Yeah.
Um, any other interesting things to note about these factors or some of
Um.
these factors?
One thing that I see is there's this one, like it looks like there's one that's a product of two twin primes. I see 31541 and 31543. Yeah, the one you highlighted too. It looks like is also twin primes up there.
Yeah, so this is a product of twin primes, and this is a product of twin primes because if you add 2 to 4998569, you get 4998571.
Yeah.
Okay, so here, let me start. My apologies to those who are colorblind, but let's start coloring. So, like, let's say I'm going to mess up these colors later on anyway, but just to distinguish them, let's say twin prime things are like green.
Okay.
And before we noticed there are some numbers that are like have a lot of ones.
Yep.
Like this thing had a lot of ones.
Okay.
Let's
Yeah.
make that like blue, and this also has a lot of ones in one of the factors.
There's sort of like an
Then if we can
intermediate
scroll up,
one down there. If you go down a little. Oh yeah, yeah. The one right one. Too fast. Hold on. The one that's one below the top blue one. Like it's not like there's a lot of ones, but both sides have like a large amount of repeating digits that are selected from. It looks like three possible options. Like the one on the right is only sevens, eights, and nines. The ones on the left is only like ones and twos and threes. I don't know if that really counts as the green pattern. It seems like a kind of pattern in and of itself.
so okay, so this has 1, 2, and 3, and this has 9, 8, and 7.
Mm-hmm.
And
That
this
one,
has
that one
1, 2,
there
and
is
3,
the
and this has 9, 8, and
yeah,
7. So there's like a 1, 2, 3, 9, 8, 7 kind of pattern.
yeah.
So that's a different kind of pattern. So these are all interesting things. Um, and
There's
here,
another
1,
one, one,
2,
two, three,
1, 1,
nine, eight,
1, 1.
seven. Yeah.
There's another twin. Oh yeah, these are twin primes. What did we say that was? That was green. Green for twin prime. And this thing is 1, 2, 3, 9, 8, 7.
Those are twin primes right under it. The next one down.
Oh, and these are twin primes right under it. Okay, this is looking good. And this is 1, 2, 3, 9, 8, 7. What's this one?
That's the ones in a two, or the ones in a
Yeah, the
nine.
mostly ones.
Yeah.
Yeah, that's like all ones except one digit is not a one.
That's a twin
Um,
prime.
but
Two twin primes in a row? No, not two twin primes.
oh, sorry. This
That one's
yes,
twin prime.
this looks like a
The one
twin
on the
prime
right, I'm
is
not
green.
sure.
Hmm. Yeah. Huh. Oh, this is 123,987.
Mm, the one
But
above
we still
that.
have some things that don't have colors.
Yeah.
So what can we notice anything about those ones that are not colored?
It looks like the digits between the left and the right side are shared. Like that one has zeros, ones, sevens, fours, and nines only. Um, on both
Yeah,
sides.
this I just destroyed it. No. Yeah, this it's true.
They look switched around.
Like palindromes.
407001 on the left half, and on the right half it's 407001. Not palindrome, but like half
Oh.
swapped.
Huh.
Yeah, so these have their two halves swapped.
Oh, interesting. Yeah. That's
What
also
about
true.
these two?
That looks like it's also true there. From skimming, I haven't actually gone through digit by digit, but it looks like it
That's weird. They're like
Uh,
swizzled.
swizzled.
That's that technical term.
Really?
yeah, so no.
It can be. I
So
mean,
yeah,
that's
so these have swapped halves.
Okay.
Okay, what about these two? Do they fit in
Um,
any of our patterns?
it looks like they're swizzled. I'm gonna
Okay,
go with
I'm gonna have to change all my notes. uh, let's see, 721. Yeah. Okay. This is 123789. This is mostly ones, which is what's that? Sky blue. Okay. And this is 123789.
Yeah.
And what about the ones at the top? We kind of skipped. This is 123789. This is mostly ones.
That
And
one's swizzled.
yeah. And this one is a twin primes. Because 11, 13.
Mm-hmm.
And
Twin
this one
primes.
is also twin prime. And this, what are these?
Swizzled. You know, what'd be
Yeah,
cool.
and this is one, two,
The
three.
top one was a set of swizzled twin primes that are made of all ones, and only have nines and eights and sevens and ones and I guess that wouldn't
That
be
doesn't
possible.
really, that's not really possible, but
Yeah.
it would be cool if
I
possible. And what about this pair?
guess that's all ones. Like the one.
Yeah.
Yeah.
Okay. So every pair of factors, so every factorization
Mm-hmm.
in this little practice that, say, Mathematica could do in a second, fits into one of these four categories.
Mm-hmm.
So I'm going to write those in the chat. A second here.
So I'm wondering
Where?
if perhaps if we actually read these color bands down from top to bottom, if that could give us any information, like if there's actually um, like a number to be read in this like column, like for example in base
So
4.
maybe, but like, there's nothing to really tell us, like, A, what the mapping to base 4
I had the
should
same thought.
be, and B, like, how we would read it.
Right.
At least not currently.
Yep. Yeah.
But we definitely do want to keep track of these categories for sure.
Mm-hmm.
But yeah, we don't really know. So I just put in the chat, we could say like, okay, there's twin primes. There's the pairs where one of them is mostly ones, except for a single digit. There's like low digits and high digits, like 1, 2, 3, and 7, 8, 9, like these yellows. And there's swapped halves, which we can call swizzled. And those seem to be the four types of factorizations that we have. Yeah, and Fractal doubts that it would switch to base 4 if everything is base 10, like 1, 2, 3, 7, 8, 9, that's very base 10 heavy, mostly ones,
Yeah.
and that kind of relies on base 10 for it to
Right.
work out that way. But, so, okay, and let's suppose that, like, we have enough data, I think, to reasonably conclude that probably the ones that were too tough fall into one of these four categories as well.
I would be
Um,
curious to. It doesn't look like any of the ones that had the large strings of repeating digits on the left was factorized correctly. Like the one with all those twos at the top there, for example. Like I would be curious to see what the factors of that one look like in order to yield
hmm.
that, because it looks like it's intentional. Like that doesn't seem to be a result of either intentional or a result of some kind of specially chosen prime.
Yeah, that is interesting. I'm just looking to double check that. Yeah, we don't have a good example among the factored numbers. Um, okay, so there are a lot of options. What do you all want to do next? And as I said, I've prepared some things in the oven. So if you have an idea, I can sort of uh, help us move along with that idea as
Well,
appropriate.
um, I mean, so one thing that comes to mind that I don't know if this is really the most time efficient thing to start with, but we could just enumerate like the ones and the two primes. Like that seems to be a very like it's there's only a relatively small amount of primes that can be written as all ones with a single other digit. Um, so like one thing we could do is just enumerate all of those up to some size, maybe half the size of some of those bigger primes, like the one that your mouse is on right now, and that could just sort of you know be used immediately to test against the smaller ones.
Okay, so if you don't mind, because I'm pretending we're on a team, I'm going to simulate, say some responses to your idea.
Mm-hmm.
So what I hear you saying is that, if we guess that or hope that a number has a mostly ones kind of factorization,
Yeah,
then it's not too bad to factor it
right.
because there's not too many numbers that are mostly ones. Is
Yeah,
that
we could
okay?
prioritize. Yeah, like if also another thing I'm noticing is that it looks like in all of these cases the amount of digits of the two primes are the same. Actually, just kidding. I just noticed the one that had 17 and 11131. But wait a minute. For all of the other ones, it looks like maybe the ones in a not one pattern does not follow that trend, but all of the other ones do.
So
Well, if
twin
we're treating
primes
it
kind of
as like constructing it, it would be like the swizzled primes. It makes sense why they would have to have the
Right.
same number of digits for each factor, and also
Twin
the twin
primes,
primes. It makes
yeah.
sense why they would have.
It appears just by eyeballing to be the case also that the nines, like 987 and 123 patterns, also follow this trend, but I don't have like
yeah.
that's just by inspection. I don't know if there's a reason that would be, but
Yeah, and so I would say, and this is typical of these sort of mystery hunt or puzzle hunt type puzzles, is that we'll have a lot of observations. And some of them might be useful now, some of them might be useful later, some of them won't be relevant.
mm-hmm.
And so I don't know that it's obvious to me or anyone on your team what we could do with the fact that all these yellow, like low high pairs seem to have the same number of digits. But
Well,
it is an observation that we'll sort of keep in our list of observations in case it's useful later.
yeah. What I was thinking is that would immediately shrink our search space, especially in the case of the ones, because like then you could just square root the number and just like figure out the amount of digits that it would have, and then like from there you know how many like what the set of ones plus a digit to be searching through is. But I guess the ones is the one pattern that doesn't hold for, so that's probably not useful.
For the yellow
Yeah,
operation, it's like I almost want to see some kind of complement to get from one factor to the other, but
Yeah,
it's
I
just
was
not
thinking the
exactly
same thing,
clicking
but
for
I don't.
me.
Yeah, I don't see it either.
yeah, it's not going to be like because they both have to be prime. That like limits the extent to which some sort of complement idea could work.
Yeah, true.
Uh, but what I think we're all discussing, and what I think we can move on to is what might be another phase of this. I'm going to switch to I'm going to change stream here, but I can copy and paste some numbers as examples if and when we need. So we have, let's see, so we have these four types of numbers. Hopefully everyone can see the text
Yep.
my new share. And so we started talking about like, how can we factor each type? Because some of those numbers were kind of too tough to do quickly,
Yeah.
naively. But if we know it follows one of these types, maybe we can factor them. Uh, and so actually, TwoSwap, you already came up with a plan for one of these types at least. So for mostly ones, we could enumerate or just test every mostly ones number as a factor,
Hmm.
and that's actually a reasonable strategy. Like if we guess something might be mostly ones, we could just try this on all of them,
Yeah.
because there's not that many mostly ones numbers up to the size of I don't know how many digits these have, like 50 digits or something.
Hmm.
That's fine.
Yeah.
Or
It that also
yeah,
seems less easy, but still maybe plausible in the uh what was it, low high, although
yeah.
maybe not for
So
the big
let's
ones.
think about let's think
Are the
about this
swapped
because for
halves
low
ones, are they a nines complement by chance? I didn't get a good look at one to test that
are
yet.
you when you say nines complement, do you mean like the individual digits are like nine minus the digits in the other half or
Yeah,
something?
yeah.
They're
No,
not
no, not that.
exactly.
Yeah, no, they're
Ah,
hold on, I'll give an example here. So swap halves. So here's an example of two of the factors for swap halves. They're not even close.
yeah. Okay.
One thing I'm realizing is like it might be possible to determine which class things are in by looking at their first and last digits. Um,
Well, that's maybe that's true. I'm not sure. I haven't given it a thought. But I
Are
will
the
say,
halves
if there's
themselves
only
prime?
four classes, we could just test them all.
yeah, I guess so. That's fair enough.
Like if we find a way to factor all four classes,
Yeah,
then we
yeah,
can just
that's the
try them
that's the big
all.
if. um,
Well, yeah, but
okay,
like
I guess
it
I
would be
guess you
good to
imply
be
that
able to
there's
factor it all.
definitely an easy way to do that.
Well, if there's not, then like I'm not sure what we would do next.
Yeah. Well, I'm not sure what we're gonna
But
do
I'm open
next anyway. So.
okay, that's
No.
fair.
I'm just
Uh,
playing with you. But
okay.
yeah.
So
I
yeah,
don't
so we
know.
have a
I guess
mostly
it.
one strategy.
Okay.
Is there any other, like, for low high or swapped halves or twin primes? Does anyone have any thoughts as to how we could have a strategy to reasonably test or to factor a number in one of those classes?
I'm thinking about the swapped halves one, but it's not coming to me yet.
Yeah, and this may not be something you
Twin
can.
twin prime should be easy peasy. You just square root it and then like check the two sides.
Okay, so twin primes. There's some sort of idea here. Something about square root.
Yeah, like you just take the square root and then like take the next odd number above it and take the next odd number below it, and then those should be the two factors, and you just multiply and check.
So yeah, just so everyone can follow along, uh, I've sort of pre-baked a little bit of algebra. So let's say our number is the product of like a prime and p plus two, and that's almost a square. And so then what we could do is we could sort of solve for the prime. The p plus one is going to be the square root of n plus one. But as you said, if we take the square root of n and we look for numbers nearby, that kind of gives us what to look at as well. Either way, but it's kind of instead of blindly testing, we could also just check: is the square root of n plus one an integer? If it is, then we know it's going to work, and if it's not, then it's not. So yeah, this is how we can test. We can handle twin primes uh, quickly. So I'm not sure. Let me scroll through 886. 1 second here. Yeah, so one of the ones that was too tough, actually, just to sort of emphasize, this one was too tough to factor.
Mm-hmm.
But actually, it turns out that the square root of n plus 1 in that case is this integer. Um,
Ooh,
and so if we subtract 1 and add 1, we get two numbers that also happen to be prime. And those are the factors of this number that was too tough.
cool.
So we have a strategy for twin primes. We have a strategy for mostly ones. Just a side comment, since we kind of figured out mostly ones so quickly. When I did this in the real puzzle hunt event, um, I thought, oh, what I should do is I should figure out like what are all the mostly one numbers that are prime, and sort of went through and tested them to get a bank. But like you don't. There's so few numbers that are mostly ones. You don't even need to do that step. You can just try them all.
Mm.
So it doesn't really matter. Um, okay, so we have mostly ones, we have a test, and twin primes, we have a test. The others are going to be harder, but I think we can do it.
Looking for like a foothold with the swapped halves ones. I'm thinking like just considering trial division. Like if you take your number n and you divide it by the top digits of one of the factors you're guessing, like it should, by the time you're halfway through the division, you should be left with a quotient that represents the bottom half of your digits. And if you have that, then you know you have the correct thing. I don't know how to do the whole like find the like just guess quickly part though. Like that's the annoying bit that I can't quite connect there. But it might, I don't know how to speed it up from there. But it does feel like it makes it simpler, no?
Well, I mean, so the thing is, like, if the number is really big, there's a lot of potential halves. So, like, I don't know. Like, there's way too many to trial divide when the numbers are getting big.
Right.
So I'm not sure I understand. I'm not sure I follow, but if I follow, maybe it doesn't sound tractable.
It's probably not like the best like potential like speed up I'm seeing here is like maybe you could get from like a up to the square root of n back to like a fourth root of n check or something. Like maybe.
I see. Yeah, I'd buy that, but I don't know that that's good enough for the larger numbers.
Hmm.
But
Yeah.
I do. Um, huh. And so the thing is, because this might be on a bigger team with some people with more programming or some more math experience or whatever. We don't necessarily have to only go with, especially if you don't have like paper in front of you and a lot of time, only go with what you're able to come up with in a very quickly. So yeah, maybe you want to like try to walk through swapped halves with like hints or like one step at a time to see what's going on, even if it's you're not figuring it all out yourself, because the real thing, you're on a team. Unless anyone has another immediate idea.
I'm down to try it. I don't have any
Okay.
great ideas off the bat.
Sure, sure. So I have this is an example I stole from the solutions, but we can hopefully explain it in a more interactive kind of way. So this is actually not, this is not a number that's on the practice, but it's just a demonstrative, like a number to demonstrate to help us figure out how could we factor a swapped halves case, basically.
Mhm.
I'm going to make this a little wider. Hopefully it's still legible. Okay, so it turns out, like spoilers, this number is a swapped halves number.
Okay.
But I'm not telling you what the factors are. But if it was a swapped half number, do you know how many digits the primes would have? Or can we figure that out?
Well, it's half. Like, so each one should have 10 digits,
Okay,
right?
P and Q should have 10 digits. So yeah, so M has 20 digits, and so P and Q should have 10 digits. I agree. I think maybe it's possible, like if M had 19 digits, it might still be possible to have two 10-digit primes.
Yeah.
Uh,
Yeah.
Not sure. But certainly with 20 digits, two 10-digit primes sounds right to me. So that's great. There's something in the chat. Uh, a Okay. Uh,
I'm gonna
all right.
drop a bit of
So,
algebra I just did in the chat.
okay, someone has some algebra that I will look for. Maybe copy and paste if the algebra is
It's not
forthcoming.
exactly copy pastable, unfortunately, because I did it in Desmos. So I will copy out the latex if you want it, though. But basically, I'm
Ah,
like thinking about how I would represent like the product of these two factors, like by construction. If I say like I have these two halves, right? They're base digits apart, b, and then I'm
yes.
like multiplying x, which is, I'm just saying the two halves are x and y, and then I'm like working out that factor. So that's what essentially that product should look like. So
Yeah. So let's
I'm
I'm gonna steal that algebra and write something that's like almost the same thing as what you said, because that's great algebra to be doing. Okay, so to catch everyone up to speed, so we have P and Q, they have 10 digits, so their halves, I can spell, which I cannot, their halves will have 5 digits each. Let's call them X and Y. And then we have, what we have is M is, in this case, 10 to the 5, X plus Y that's like P, let's say, and then Q is 10 to the 5, Y plus X. And then we can expand this, and this is sort of what you were saying, is 10 to the 10 xy plus 10 to the, where my 10 to the fifth is your b, I believe. But I think like sort of by
Yes.
doing this example,
Yeah.
we'll understand the general thing. So we expand that out and we get this algebra. Um, okay, that's some good algebra that will be helpful. And so to write out this algebra in our particular case, to help us understand things better, what I'm going to do is I'm going to say, let's say xy, because we have an xy over here and we have an xy over here.
Yeah, we know what
So
XY has
xy
to be
seems,
by the end 5 digits. If wait. No, you
so
don't.
yeah,
Uh, I
yeah,
think
so
you do
I
know
think
this,
you're thinking,
but yeah.
you're doing some good thinking. So I'm going to write some steps that will help get everyone sort of along the same train of thought that you have, which is exactly a good train of thought to have. So let's name these. I'm just going to say, okay, X, Y, it's like A, B, C, D, E, F, G, H, I, J, or something like that. Um, because X and Y have 5 digits, so the product is probably has 10 digits, or maybe A is 0, maybe it only has 9 digits. I don't care if A is 0, that's fine by me. Um, and so if XY looks like that, this sum that we just wrote with the algebra, that 10 to the 10, blah, 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 what does that look like? That looks like, and this is why I bake this in the oven,
Oh, okay. Yep.
that looks like
Yeah,
this.
right.
So we have a
So
sum
we
that
can basically examine and get the factors then, right?
We can figure out A,
In
B,
a lot
C,
of
maybe.
cases.
D, and F, G, H, I, J. I think. I think E might be tricky.
So yeah, let's think about this. So on the right side, which is what you said first, we have, or second or whatever, we have this FGHIJ plus some zeros is 28241. So we know FGHIJ just from that part of the sum. Uh, and this middle part with these question marks, I don't know off the top of my head what x squared plus y squared times 10 to the fifth is going to be like, except that it ends in 5 zeros. Um, so yeah, it would help if I knew like how big, like how many digits, how many of these question marks could this 10 to the 5 x squared plus y squared actually take up? Um, does anyone sort of know off the top of their head?
Well,
Well, X
X
and
and Y
Y
are
would
both 5 digits, so I mean it's gonna be something vaguely like uh
15 digits altogether
15
after multiplying by
digits
the
that end
10 to the
with the
fifth.
with all zeros.
So yeah, we see the zeros. So like 15 digits. Um, so but like if x and y are big, could there be like some carrying
Yeah. That could be
when
there
we
could be
add?
like there could be like like x
A
squared plus y
16th
squared
digit.
could carry over. That's why I said e would be possibly hard.
Yeah. So I'm going to write what we said in sort of inequality. Sorry, x squared and y squared, they're both less than 10 to the 10. So x squared plus y squared is definitely less than like 2 times 10 to the 10. And like you said, we can uh, multiply this by 10 to the 5. Let's see here. 10 to the 5 times this thing. We just make that 15, like that. And so like there could be a 16th digit because of this. And one thing I'm going to do, because we already handled like this xy at the end, we already got our last 5 digits of the product out of the end of m. So what we could do is we could sort of add that in there. So what I'm going to say is I'm going to say if you add in that other xy, well, we know xy is less than 10 to the 10 for sure. Because x and y only have 5 digits. And so this whole thing, in the absolute sort of worst kind of carrying case, is still less than 3 times 10 to the 15. So I did that algebra kind of fast. So take a second to look at it and see if you believe it or if you have questions about it.
That makes sense.
Yep.
Okay, so if we write that in our sort of summation thing, we can write it like this. So we have some question marks in the middle, and then this sort of 16th digit, we know it's less than 3. Maybe it's a 0, maybe it's a 1, maybe it's a 2 in some really bad case. That's kind of as bad as it could be. We know FGHIJ is that 28241 at the end. And so we can see now that we've done those inequalities that, like 2Swap was saying, the left side almost gives us A, B, C, D, E. We either have A, B, C, D, E, or we accidentally added like 1 or 2 to it. But that's it. That's all that could have happened.
So that's easy to check.
I'm imagining the jump
Yeah, so X
to a complete factorization algorithm is rather simple. Once you figure out like A, B, C, D, and F, G, H, I, J, then you only have 10 guesses to make for E, and at that point you can just factor it and find X and Y. And I think that's a
or actually we know
fourth root speed up. If I'm not mistaken.
Yeah, we don't even need to. Well, we can do better than the fourth root thing actually.
Okay. Cool.
And also we know that this sort of E is only off by up to 2. So like 3 cases instead of 10 cases, that doesn't really affect things too much. It's just a fun fact. But what we can do, so we have 3 possibilities for the product of X and Y. But we know something else. So this is one equation in X and Y. But we have another equation in X and Y. We have the equation with M. So mathematically, we have these 2 equations in X and Y. They're quadratic equations. So we can solve these 2 equations with like the quadratic formula.
Sorry, remind me what M is? M is the original prime that we're given. Is that right?
The original number that's semi-prime. So yeah,
Okay.
M is this.
Yeah, the semi-prime.
This semi-prime thing. So we can solve these 2 equations for X and Y. And so if anyone doesn't believe me or needs some sort of convincing, what we could do is we could take this M equation and we could rewrite it as x squared plus y squared. We could solve for x squared plus y squared. That equals m minus, in this case, 10 to the 10 plus 1 xy over 10 to the 5. And so we have 3 possibilities for xy that we can check. And so that gives us the 3 xy values. Values give us 3 values for this sum, 3 for this. There turns out to be this. Or these other numbers, doesn't really matter what the numbers they are. And then, well, this is almost enough to solve because x plus y, just sort of algebraically, is going to be the square root of x squared plus y squared plus 2xy. So algebra
Yeah.
is helpful again. So if you know xy and you know x squared plus y squared, you can get x plus y. And so x and y, this is more algebra. Maybe you'd have to ask the math person on your team about this. Are the roots of, let's say like z squared minus x plus y, z plus xy equals 0. So if you have the product and you have the sum, you can set up a quadratic equation to solve for them.
Mm-hmm.
And so yeah, so the idea we had above about the last digits and the first digits give us only 3 possibilities for xy, from which we can read off the 3 possibilities for x squared plus y squared and get a quadratic, and we can just solve the quadratic in all those cases to see what we get. And so it turns out in this case, xy happens to be the one with the 3 where there's carry digit of 1, and x is 61653, and y is 84397. And so, the math people on your team, they do this algebra, and they learn this idea for finding the halves based on the quadratic formula and this other stuff that we did. And then maybe they hand it over to a programmer because maybe they don't program. And the programmer writes out the program that takes a number, sort of cuts the size down into quarters and reads off the digits at the end and the beginning and the cases and solves the quadratic and tests them for integers and factors.
Cool.
And that is a lot faster than the fourth root idea.
Yeah.
Yep. It's in like basically constant runtime if you pretend like integer multiplication, etc., is like instantaneous.
Right.
Yeah, this is real fast. But we had to do that algebra to know how we could do it.
Mm-hmm.
Okay, so mostly ones we could do, twin primes we could do real fast, swap halves, also kind of like a quadratic kind of thing, turned out. Now, the last category. Oops, I keep doing that. So low-high, so one factor has 1s, 2s, and 3s. 1, 2, 3, and the other has 7, 8, 9. And as I said before, just to remind you, there are a lot of, like, if a number is pretty big, there are a lot of numbers that have 1, 2s, and 3s, like 3 to the length.
Could I?
So
I have an idea. Could you go back to the last, like the page with all the numbers on it, the spreadsheet?
Yes.
I'm wondering if like we could read from like right to left, and like for example, if the last digit is 9, then I think that like the last digit on the like you're left with like the pairs like 1, 9 and 2, 9 is the low high pairs, if I'm not mistaken.
So 2 times 9 is 18, so 2 times 9 isn't even possible.
Did I say 2 times 9? I meant 1 times 9 and 3 times 9. But no, 3 times 9.
3 times 9 ends in a 7?
7, yeah, that would end in a 7. Wait, so
yeah.
you only have 1 times 9? 3 times
that is true. If it ends in a 9, you only have 1 times 9. It's a great observation.
Okay. Is it like one last digit would correspond to every possible combination of
I don't have Gray Cuber here to help us with modular.
Like 1 times 7 would give you an ending 7, and 3 times 9 would also give you an ending 7. So I don't think it's like that easy.
Yeah. So let's go back. Let's note that. I'm going to go back to the other share if that's all right. But I do like how you're thinking.
Cool. Yeah. Go for it.
So let's change stream.
Attempt to like do one right to left, but I'm already half stumped.
So so what you're observing is if we look at the last digit of each number, here's a little table of all the possibilities.
Yeah, cool.
Pre-baked. And so, 1 and 9 is the only way to get 9, but 7 can be gotten as 3, 9 or 1, 7.
Right.
And 8 can be 2, 9 or 1, 8. But it kind of, limits the possibilities decently to like a couple for the last digit of each
Yeah.
of them.
If
Um,
if we take the last
okay,
two
so let's say
digits,
we,
I'm wondering what we then arrive at.
yeah. So if we take the last two digits, we could, use modular arithmetic or just dividing in remainders or however you want to think of it, just like multiply out all the relevant products of two digits that end in the right way. So like if the number, let's say the number ends in a 7. So we know it's 17 or 39.
Yep.
Then in each of those cases we could see what tens digits can we add to get the right two digits at the end.
Yeah.
So here I'll write out an example. So like let's say the number was, I think this is on the practice list, 1 7 4 7 4 7 3 6 4 7. So that ends in a 7. So we know that the two factors, if it has this form, this low high form, the two factors are either end in 1 7 or they end in 3 and 9. And then for ending in 1 7, what are our possibilities to get to something that ends in 4 7? Uh, so to end in 4 7 from 1 7, you wrote some code, and it turns out the only thing is 1 1 and 7 7.
Hmm.
And to end in 4 7 from 3 9, the only possibility is 23 and 89. So before I move on, does anyone have any questions about what we're doing here with these last digits? Okay. Um, so yeah, so what we can do, and this is something, the previous thing was really algebra heavy, and you could kind of do all of them by hand with that algebra. This approach kind of really needs a program because you don't know what cases you're in. You're going to have multiple possibilities some of the time, but there's not going to be too much branching because the end of the digits of the number really limit the end of the digits of the factors when they only have low digits and high digits.
I'm trying to build a like digit by digit algorithm in my head, starting from the right hand side of it. I like running it in my head. I'm not exactly convinced that the blow up time is manageable for large numbers.
Well, the great thing about this is, maybe you're a little skeptical. Your teammate writes it and it seems to work great on the numbers. Uh, that's the kind of thing that can happen.
Right.
So, like, it turns out because if you have a fixed, like 23 and 89, there's like there's not. Well, this little table for the last digits kind of shows us hints that there might not be too much branching, and it turns out in practice there's not too much branching. Um, it tends to work out, or maybe they chose examples where it worked out nicely and it doesn't always. I'm not sure, but it really there's very
Hmm.
often not many bifurcations.
Okay.
So, for instance, for this example, which is a real example, uh, you keep going, and each of these paths, the ending in 1 7 and ending in 3 9, they actually don't bifurcate by the time we learn what the factors are. So on the 2389 path, it gets 1 2 3 9 8 9 and 2 1 3 8 9 8 9. And then you find out, oh, we have the factors. They're 2 2 1 2 3 7 8 9 8 9. And the other
Okay.
path ends up going 3 1 1 7 7 7 and 2 3 1 1 8 7 7. And then you do get a pair of 5 digit numbers that ends in the same 5 digits, but these are the wrong factors. The other ones were the factors, and then you can just check that.
Okay. I could be convinced that this is like a polynomial time thing,
Yeah.
at the
Or
very least.
and as I said, maybe the numbers are carefully selected so that it doesn't grow too bad. I'm not sure, uh, but from having solved this puzzle, I know if you write this program, it works out pretty well on these numbers.
Okay. I
Um,
believe you.
okay, so we figured out a reasonably efficient approach for these 4 types of numbers. So let's go back and look at the puzzle. Let's say we have those in hand, and we have the program ready to go and to throw numbers into. And like I said before, we could just sort of, if we don't know what type of number is going to be, we just try all 4. All 4 approaches. One of them hopefully will work. So can everyone see the table of numbers again?
Yep.
Yeah.
Yep.
And so that's great. And so, we could do that and we get all the other, we fill in all the 2 toughs. They're all in one of those 4 categories. But I already forgot, what was the original puzzle again? You could try it on the big N at the top. None of them work on the big N at the top. So it's not like, the big N at the top was just a product of twin primes or something. It's not that simple. So we solved all the factoring practice. But I think we kind of forgot, or I kind of forgot about the extra practice. So the extra practice has these huge numbers, and there's 4 of them. Does anyone have any thoughts about that?
Well, maybe it's one of each type.
Yeah, maybe we have 4 types of numbers, and there are 4 numbers at the bottom. And so we could try our 4 methods on these. And either to surprise or not surprise, depending on how you were thinking about it, they work. These numbers are really big, but those approaches are so efficient, and these numbers are secretly of those 4 types that we find their factors as well. So my sort of next pre-baked sheet, or after this one, we've done all of them. So here's all the practice, and so here we can see, like, okay, we have low, high, and halves, and ones, and twin, and I use different colors here, but that's fine. I think you can get the idea because we have the column B that tells you what type we have. Oh, actually, this is, you can't even see the other factor. Why can't you see the other factor? Because the extra practice numbers are so huge that one factor is like the entire screen, and then there's the other factor. But we have it. We have these numbers. Hooray. Also, what? What can we possibly do with these numbers?
Wait, so hold on. So to be clear, like on the top number, when you said it didn't work, you meant it didn't find the solution, not that it didn't find it in time. Like was it just taking too long, our approach for whichever one was the correct one, or was it just that it?
Yeah. This capital N is definitely not a twin prime, and is definitely not swapped halves, because like those we have like finite possibilities for those.
Mm-hmm.
And I think, yeah, just like we saw one path didn't lead to an answer, I'm not certain, but I'm pretty sure that like the low-high approach will conclude that this is not a low-high number, because you'll get to the point where you match numbers up to like 140-digit low highs, and the product isn't n. So it's not that either, and you can try all of the 140-digit mostly 1 numbers, and those are not factors.
Okay.
Like, all of those are reasonable to do. N is not any of those types.
Okay.
Good to confirm that.
Yep.
Okay.
We might be able to get one
so
of the
here-
factors if we solve everything in the puzzle, depending on how we read it.
So yeah, we learned about all the types, and we factored all these practice things, and also we factored these extra practice things at the bottom. And so those extra practice things at the bottom, they're separated out, and there was one of each type. That seems to suggest they're extra special.
Well,
but
sorry, go ahead. I'll mention.
No, yeah, but like, so let's think about it. Like, and I can scroll to the other factor if you want to see the other factor. But we'll need to come up with something.
The one thing that we haven't used, the one piece of information that we haven't used so far was the repeating digits in the primes themselves. I don't know if that tells us anything. I also don't know if in n there are repeating digits, because I don't think I actually like stared at the n itself for a long time. But that could be a bit of information that we're not using.
So you want to look at, so n, here's n.
Okay, no
repeating. It has like a couple, there's like triple 1, triple 2. I don't think there's anything more than triple.
Gotcha.
in n. And here this has all the other numbers.
Okay.
So yeah, you noted like some of these. Where was the one? Here, I'll go back to this other sheet here. So like this one, row 37 or so, has a bunch of sevens. Let me find that over here. So this one. So this one has a bunch of sevens in the middle, and you were wondering about it.
Mm-hmm.
It has a bunch of sevens in the middle because it's a mostly ones number, probably. Because this mostly ones is much longer than the other factor. Like this is a much longer prime.
Right.
Yeah. So here yeah, and so that's going to generate repeated digits.
Okay.
One thing I will confirm, your observation earlier that the low-high numbers had the same digits in their factors. For all of the practice, the ones that we couldn't do before, that's still true. Which is interesting.
Might have the same digits in their factors.
So like this number was too tough before, but now that with our low-high algorithm, we learn, oh, it's this like 20-digit number or whatever times this 20-digit number or whatever.
You're
They're
saying
the same
low
numbers
and
of
high
digits.
don't include like fours in them or sixes as highs and fours as lows. Is that what you're saying?
No,
No, I think what they're saying is there's still equal amount of digits in each factor.
Oh, okay. Gotcha.
I think that's what.
Yeah. You observed that the sort of low-digit, high-digit factorization examples had an equal number of digits in each factor for the ones we knew about before, and now that we've done all of them, that's still true.
Cool.
We don't have a counterexample. That's
Gotcha.
just curious. Okay. So that is some stuff, but now that we've finally factored those big numbers at the bottom of the extra practice, it would be good if we could figure out why we care. Like, what did that do for us? Because the n at the top was not any of the four types. Here, I'll stick with. Well, I can go back and forth, but I'll stick on this screen until someone tells me to go to the other factor. And this is a sort of thing where. Oh, here, let me give us a minute to think about it, because this is something where maybe anyone could chime in with an idea.
I mean, maybe there's some way to read. I mean, maybe we should just count digits on these to see if there's some way that we should be combining them to come up with another special number to factorize n. I don't know if that's a workable idea or not. It's just an idea.
Can we do trial division on n by all four of those answers?
So these, I believe none of these primes have exactly 140 digits. In fact, they have far fewer than 140 digits. So it doesn't work.
Is there any chance that they have like 70 digits so that we could read two of them concatenated or something? Or am I barking up the wrong tree?
I mean, that's a fair idea. The two concerns I have with that are one. So one thing for these puzzle hunt things, especially something as well crafted as the MIT Mystery Hunt, is that they're crafted with a lot of intention and testing. Mm-hmm. And so if we only needed like two of these extra practice things to find out the factorization of n, it wouldn't be a great puzzle. Like if we never figured out swapped halves and could still answer it,
right?
That would make it like an imperfect puzzle. So it's not likely the solution is that. And let's just say you try it for the heck of it, it doesn't work.
Okay.
If there's one of each type, there must be something relating the answer for that type with maybe all the answers of the same type.
That is a good thought. That is the type of thing that would not be uncommon in a puzzle like this. So let's keep that thought. But I don't know as of just yet what relationship we could possibly use. And so I think instead of dragging this out, I will say that if you're on a team, even if you're new to puzzle hunts, you'll be on a team with others who have some experience with the common tips and tricks for these things. And in fact, I have a tab right here of like resources for beginners that will have some basic tips and things like that. And so, one basic tip, which I will be happy to reveal because you almost certainly have someone on your team to reveal this, is that if you have numbers and you think there might be a message, there's something that is pretty common. There are a lot of common things that come up, but one is, does anyone know the @bash cipher?
I don't.
I'm
Okay.
not familiar.
So the @bash cipher is, you might know it by this name, it's sometimes known as A1Z26.
Also don't know that.
So, okay. Well, the alphabet
Oh,
starts with
that's
A,
a classic. Yeah.
ends
I
with
see.
Z,
We're just counting them.
and if you have a number between 1 and 26, you might convert it to a letter by saying, okay, 1 is A, and 2 is B, and C, and 3 is C, etc. That's a cipher.
Okay.
And so, if we're looking at these factors, not going to be able to do anything like that with like the 1, 2, 3s and 7, 8s and 9s. They don't make numbers like that.
Right.
But if we take this, what was this? Twin prime here. This twin prime begins 23, 18, 9, 25, 28, 5. It is very suspicious and would be clear to someone more experienced with puzzling that these pairs of digits are less than 27?
Yep.
And more than 1? So it seems like this is spelling something, maybe. And similarly, this other thing, I swapped halves, also looks like it could be spelling something. And for the mostly ones, this all 1s and a 4, that doesn't really say anything.
Yeah, that would just be K over and over and over again with whatever the.
But
however
this
you grouped it
other
up.
factor
Ooh.
is also has a lot of numbers that are less than 27 in it. So that's really cool. I'm going to copy and paste from my pre-baked oven sheet. Give me 1 second to switch streams here, because that is well, that's a thing to try, and then we try it and we do get messages. So let's see. So extra practice. So the twin primes, the primes here are these huge numbers, and if you do that @bash cipher, so there's 23 that the both primes start with, and then 18 that's W and R, and you get this thing, and then some of these at the end are not between 1 and 26.
Write these in base 36. Just base 36. Stop just before the first non-letter.
Yeah. So to go back to the suggestion from Cyberpunk a minute ago, now that we have this message, it seems like this is an instruction for what to do with the twin primes in the other regular practice list.
Oh.
What we should do is we should, I guess, write those factors in base 36 and stop just before the first non-letter. And if you're... So it might not be clear what exactly that means, or just to make sure we're all on the same page, I'll give an example. So this long number was one of the practice numbers, and it's this product of twin primes. And if you convert, one of these factors, it doesn't really matter because the end is off by 2, to base 36. Now, if you think about base 36, after 9, you go A, B, C, D, so you get letters out of it. Then in base 36, this factor happens to be WHEACCESSIBLE4B. But the instruction said stop before the first non-letter, so before the first non-letter, it's WHEACCESSIBLE, which is almost a word. So that's cool. Does everyone get what just happened here? We took the extra practice number that was a twin prime, we read it with that cipher, it gave us an instruction that we could then apply to, say, a number from the practice that is also a twin prime factoring number. We get some confusing letters out of it.
That makes sense. Let's say we do it to all
Alright.
of them. What are the
Yeah.
what's the
So I'll
process?
do it for all of them after we go through. Let's go through the instructions for all the extra practice, just because that's what I have
Okay.
more easily prepared. But we will do it to all of them. So for mostly ones, like I said, the factors, we have a mostly one factor and then this other factor. And again, we translate this other factor into letters, going pairs of digits. And this actually doesn't have any junk at the end, which is... sorry, I misspoke. It does have some junk at the end. But the junk at the end, just like the other one... So this other one had 9900 as a nice, like,
Yeah.
dividing line after the message. And this also has a 9900. It's very cute that they prepared it that way.
Right.
So what does this say?
Right. Factors like this one in ternary then read 2 as a dash and 1 as a dot. So I guess it's Morse.
Yeah. So great job thinking about that. So here's an example from the practice. It factors this way. And so it says it says factors like this one. So when they say factors like this one, I assume they mean the one that's not mostly ones.
Right.
And so if you convert this one that's not mostly ones to ternary, you get this thing. And if you write 1 as a 2 and 1 as a dot and 2 as a dash and 0 as a space, you get forget about this verb stuff. This is if we're making a PDF. You get this, and as you correctly point out, and if you didn't, someone else on your team would. That's got to be Morse. Morse code is Morse code. This particular example is Morse code for U.S. president. So we also get a little message from things. So it seems like the rule is these big extra practice things give us instructions for how to get messages or something. I don't know what accessible is out of the factors. Let's do the next one. Swapped halves. So for swapped halves, here are the factors with a colon between the halves, and you can read this in the same way, and we get this. What does this say?
Take difference between the halves, then use the T9 phone keypad code.
What the heck is a T9 phone keypad code? Does anyone know?
It's
like
with the letters under the keys where, yeah.
So like I don't know any examples, but like you press like 2 a few times and you get a C or something. Like maybe if you push 2 like 3 times.
Well, so yeah, here's a little subtlety that you either from experience with puzzles or by being old enough, you would remember. There are two different ways. There are two different natural ways to get letters out of this keypad. One way is what you said, like hit 2 3 times to get the letter C. But that's a real pain if you've ever done it. Like it takes a lot of tapping. And so it turns out the thing called T9 is basically predictive text. You type 2 once and 3 once or whatever, and it gives you a list of the most popular word and then the next most popular word to scroll through. That's what T9 is, actually. So, I'll give you an example from the practice. So here's a number from a swapped halves number. It factors into this. The difference between the halves is 448. So 448 has a lot of possibilities because 4 could be G, H, or I, and 8 could be T, U, or V. And so in T9, you would press 448, and that could be any of these possibilities. But for this list of gobbledygook, there's actually only one common word. The only common word for 448, if you were typing in T9, is hit. So that's the instruction here. Use this old phone message system to get words. But that's a real pain. Even if you used to do it, it's a real pain because there might be. So for hit, there's only one possibility. But like, what if this was a longer thing? There's a lot of possibilities. Turns out there are multiple websites that will make this easier. That people who do puzzle hunts might know some of them, and so there's a website you would just plug in 448 and it would just tell you hit immediately. So it's actually not that bad if you use a tool. So yeah, Google, if you Googled like T9 decoder, you would find it. So that's what we can do based on the swapped halves things. Any questions or comments about that? The last one seems to, yeah. So here's I'm just going to give you the factors for the low-high ones. Here are the factors for low-high. And so we can't do A1Z26. We can't get letters out of this that way. They do look kind of symmetrical. So when you say symmetrical, I think I know what you mean, but I want to be.
It looks like up to the. Like if we subtract, like, for example, 6 all the way to the end from the last one, it almost looks like it's going to be equal to the first one, except for the last chunk. Like, for example, the 21112, that's like maybe 20 digits in or so, looks to match the 87778.
Yeah. So if you check, this is not easy because this is not fixed width, but you paste it into something else that's fixed width, and you learn it's not quite the same. There is actually one more 7 at the beginning of this than there are ones at the beginning of that.
Okay.
But otherwise, what you said is true. So in the interest of time, I'm going to say that based on that observation, your teammate says, okay, well, if there's one more 7 at the beginning than one's there, exactly how many 7s and 1s are we talking about? So this first one has these runs of 1s of these lengths, and the second one has these runs of 7 of these lengths. So it's almost the same. And then you have the garbage at the end, like you said.
Okay, so maybe we can read that as a word.
Yeah, so if you...
Cipher, A1Z26.
Yeah, so using that cipher on these lengths of runs, we get these two messages.
Ooh. So
I'm going to give you... So here's an example of a number from the practice. That's a low-high factorization. But the only instruction that they were able to fit in those long numbers is X chords and Y chords. What should we do? And I think someone is typing, so maybe there's an idea in the chat. Yeah. So if we consider, because these have the same length as you observed ages ago, we can pair them up as coordinates like this. And if we graph the path through these points, we get file not found, which is very exciting because the page doesn't work this way. But we actually get this thing.
Okay.
What's that?
T.
And just because this is not something that you could easily do in Google Spreadsheet, I'm going to say, okay, and then we wrote a little program to take the coordinates and graph the path through the points for all of these low-high examples from the practice. And when we do that, what we see for all of them together is this. So, which look like letters like TFTN, YFIR, SDAI. That doesn't really spell anything, but at least each one gives us an obvious letter when we plot the path. So
Prop 13, maybe.
You try it; it doesn't tell you anything.
Okay.
but we have letters. So what I'm going to do is I'm going to switch back to the spreadsheet. Now that we have 4 like decoding rules, I'm going to say, okay, we did it all. Let me swap to back to our sheet here. Can everyone see that? Yes, good. So we did it. So for instance, like the mostly ones things, here's a ternary. All the letters, sorry, the letters that are drawn are in this column of drawn letters. They were T, F, T, N, Y, F, I, R, S, D, A, I. In this order, this is the order from the practice that these rows are in.
Ooh.
So
This
here,
looks
if
cool.
I can type them if you.
So is this gonna be like? Are we gonna read it like as a long message, like letter by letter?
Yeah, that sounds well. We could read a long message letter by letter if we could get letters out of the other stuff.
Right. I'm assuming.
Yeah, like we got U.S. president and we accessible, um, and the T9 stuff gets us. We saw a hit. And we get ring in perfect fourth and oxygen, capital of Florida, and so these other these Morse things are like
Tallahassee.
Survivor season name and Santa's reindeer and halogen
Like, I
and
mean, it looks like
Eon
trivia
produced.
questions.
Yeah. And so that's a thing about puzzle hunts is that it's not just like math or programming. In fact, it's often neither of those, but sometimes trivia is part of it, or wordplay, or both. Um, and so we have a lot of now we have a lot of things to look at. The drawn letter, it doesn't spell anything, but like that we just have those letters. Maybe there's nothing more to do for that. But for the rest, I think there's got to be more to figure out here. I can scroll through, but does anyone have any ideas about anything on screen,
Well, I mean, we could just
or want me to
try
scroll?
and answer the questions. I mean, what I was guessing, which might not be correct, is like we would read, just going down the list, we would like read each letter in order. So like for example, if you scroll up to the top, it would be like T H I T. I think from like the drawn letter T, then H I T, then whatever the like if it's a trivia question, just solve the trivia question and put that in the string. But it looks like T H I T
Sure.
W F
Okay.
wouldn't
So
work out. So
yeah. So solve the trivia. So solve the trivia question W. Solve the trivia question U.S. president. Solve the trivia question we accessible. Like
well,
I
I
don't
mean,
know.
I was saying like the ones that look like trivia questions, solve them as trivia questions, and if not, just read it into the string. But maybe that doesn't make sense. I don't know, unless maybe it's a U.S.
Yeah, I
president
will
whose
say
name
that.
starts with a W and went to a Summer Olympics host city or something. I don't know.
Yeah. So I will say just from like the intuition of someone who has done a lot of these before is that probably if all of the these low high things gave us a single letter, probably there's going to be a way to get a single letter out of each of these other rows also, and then we could just read all the single letters. That would be a very nice hope. But
You're saying hit
the
is
question,
going to map onto a single letter?
it would be nice if it did, because then we could say T, the letter for hit, and then like the letter that this W clue corresponds to, and then F, then the letter that the U.S. president clue corresponds to, and the letter for we accessible somehow. Okay, so
Wheelchair.
if you read
Is
we
it
accessible into
possible?
the string,
Wheelchair.
which common
accessible?
words end in WH to make wheelchair accessible? Okay, I'm gonna write that down because that sounds like a phrase that exists. If I can spell wheelchair accessible. And I'm gonna what I'm gonna do.
LCHAIR L chair. I guess that doesn't really mean anything to me.
L chair. Okay, those are the added. That's the added part.
That's the extra bit.
Does that mean anything? Does that mean anything to anyone else, or suggest anything to anyone else?
I recognize it, but I don't know what it means in another language. I think
it is not Spanish for the chair. Also, What about some of the other? Let's focus on the red ones since we got a foothold, maybe like
Baltimore
wheelchair
Orioles
accessible.
looks like the next one. The next one looks like habeas corpus. Um,
Okay. Does anyone know how to spell habeas corpus, or we just Google it?
Habeuscorpus, I
Nope,
think.
that's wrong. That's why you Google
Shoot.
it.
Okay. Do not know that one.
Um. Okay. So Baltimore Orioles. What did we add? We had Baltimore
More or
more
or.
O,
Oh yeah. No, you're right.
and then we have Orioles, and then habeas corpus. We have habeas
ASCOR.
COR. Yeah.
Hmm.
Okay. Um. Okay. So Elchier, more O, Ascor. We could do some more, but maybe someone has ideas from these three.
I got nothing.
Well, let's wait for other people to give it a second.
Uh,
I'm thinking
Also
about
got nothing.
as a parent. Um,
Um. Hmm. Okay. House is a parent.
metal
Uh,
detector.
ooh, good.
okay. Let's try metal detector. Metal detector. And so that's going to be metal
I'll bet.
detect. Yep. Like that.
Yeah.
Okay.
CRT doesn't look like enough
Maybe
information.
court for CRT under it.
Port. Like that.
Yeah.
Okay. I don't know. CRT is kind of vague. What about this
Binomial
one?
Binomial
theorem.
theorem.
Binomial theorem. We got math people here. Binomial theorem. So what do we have there? We have binomial THEO. Huh. I think I got that right. Binomial. Yeah. That sounds right. Uh
Trade
TRD.
or no?
Yeah, there's a lot of words that have
Toward.
TRD.
Toward maybe. TOWARD.
I mean, it looks like there's two classes here. There's the ones that are obvious puzzles and the ones that are not, that are just like a few letters.
Bueno. What about this one?
Buenos Aires, Argentina.
Okay.
So
So that's going to be
AIRESAR. Or wait, no, IR. No, I think the first letter's not an A.
Buenos. Oh, right. I see. You're correct. Buenos
Uh,
Aires. R.
A.
Like that?
Yeah.
Okay. So here, what I'm going to do, because this is kind of hard to scroll through, how do I turn on filtering? I'm going to filter to the twin primes. Okay, here we go. This is easier. All right.
Lieutenant governor.
Good.
Okay. So yeah, lieutenant governor. So lieutenant governor, like that. Yeah.
Ganda. I don't know what would go between
Ganda.
aiding and abetting, but that's only
Ah,
at the beginning.
aiding
Oh yeah.
and abetting. Okay,
AIDIN.
so yes. Okay, so we have a lot of these. Maybe not all of them, and there's some question marks, but that's fine. It's because if we have most of something, then like that could be most of a message, and we could probably figure it out in the end.
Mm-hmm.
But we gotta. What do we do with this column of like random letters? Uh, gonna give you a minute to make observations, and then I'll bring in a imaginary team member.
There's a lot that are either 5 or 6 letters. In fact, they're all 5 or 6 letters
True.
without including the question marky ones.
That's true.
Oh, just kidding. L chair is 7 letters.
Yeah. Okay, you're right.
Um,
Does anything look like anything, or make you think about anything else?
I'm like trying to see if there's like
Anagrams, maybe?
yeah.
Yeah. Tango at
Anagrams.
the bottom, maybe?
Tango at the
is it
bottom.
the NATO alphabet?
It is the NATO alphabet. Great teamwork. So someone recognized anagram, someone
Oh, that's
recognized the NATO
Delta.
alphabet. That's Delta. So L chair.
Nice.
What's L
Charlie?
chair? Charlie. And so what you could do, even if you don't know it off the top of your head, you could pull up a list of the NATO alphabet and figure out that this is, Romeo.
Oh
And
my
this is
gosh.
Oscar.
Right.
And OU is not going to work. But this is India. And this is Sierra. And figure out some more, or maybe use the list, or maybe even write a program to try and like take anagrams and fill in some of these. But like, so now you have the idea, and so this is a way to get single letters out of the nonsense like we accessible,
Right.
the NATO alphabet. Okay, I'm gonna you hand that off to someone who's good at wordplay and NATO alphabet, and you don't worry about it. Like they'll solve it and come back to you.
Okay.
Okay, and we did the low-high graph. I already wrote the program and showed you. Look at the ones, for instance. Oops, that's a little hard to. I don't know why. Whatever. Okay, so this ternary for one. That's just for the Morse code. So I'm not even gonna. I'm gonna hide that column. I don't even want it. But we have. Here, this is and I can show an example factor. So we have all these messages like month and Super Bowl winner and Greek letter and Eon produced Bond film and halogen, U.S. president. And remember, as we said at the beginning, like certainly, Google is allowed. So if you want to Google like what are all the Survivor season names, you can absolutely do that. The Eon produced Bond films. But
wait, sorry, I didn't even realize you're suggesting that the thing with the ones is going to be like part of the puzzle. I assume that was like the extra buffer that they needed to be able to come up with a prime.
Well, for the extra practice, we only read the other number, and it said like for ones like this, convert it to Morse, basically.
Yeah.
But like, yeah. So I don't mean to imply, that here's other numbers.
Well,
maybe we did this. Well, we converted the numbers in column C here to Morse already,
right.
so those can't be relevant.
Yep.
The ones with the ones either may or may not be. We don't know.
Okay. So I'm thinking like, I mean, there's always two parts. There's a beginning part of a section of ones, and then there's an ending part, and then there's the middle number.
Yeah, and we have these messages here, like month and Japanese prefecture and rainbow color.
Well, so okay, rainbow colors looks easy. We could just go through the list. I'm trying to see if there's like, just starting with red. It doesn't look like red has any particular affinity with 1111151. Like violet, VIOLET. That doesn't match the number count or anything.
Wait, so
there's 7. Roy G. Biv is 7, and there are 7 digits in that factor, are there?
That's a good observation.
Oh.
So hold on. So there are 7 rainbow colors, and
So is that
1111151 has 7 digits.
Yep.
Is that a coincidence? Let's look at some other one. Like how many months are there?
12.
In this
And this is
context,
12 digits.
indigo would be highlighted by the 5, the way I'm reading it. So.
Yep.
Okay. So indigo is highlighted by the 5 because it is the 6th of the 7 rainbow colors.
Yeah.
And so what?
April.
What do we get
for month?
So January, February, March, April. So the April is the month. April is the 4th month. So yeah, Roy G. Biv, indigo is a rainbow color. Because indigo is the 6 out of 7 rainbow colors.
I'm
Okay, now I
unclear
can get it. I
order
think
of
now.
them.
I forget the order of Santa's reindeer, but I think we've got the plan of
So
attack for this one.
so we have a word here, January, February, March, April, like this, and we could fill in a reindeer, and we could look up like halogens and Bond films, Greek letters and stuff, and
Wait,
pick out
wait,
things.
I kind of want to do this part. Shoot, I want to just skip over. That's okay. That's okay.
Yeah, no, we can skip over most of it, but there's a there's one thing
This looks fun as hell.
that I'll kind of like skip ahead to because this is very artificial. We might not solve it in the order that you would in real life. But so we have April, we have Indigo, we have things like that. So we're saying that like the month is A and the rainbow color is I, and that's where we're gonna get the letters.
Seems plausible.
Okay, so we do that, and we solve the last thing that we haven't done yet, and we kind of get nonsense. Those letters don't work, actually. Even though there are definitely 12 months,
You're
and
saying if we
April is the
read
fourth
from the
month.
top to bottom under those question marks, the first letter, and it gives us
Yeah,
nonsense.
that doesn't. That ends up giving us nonsense when we solve everything else.
Well, maybe we should just do a few more and see if there's a pattern.
Uh,
Like, besides April and Indigo, like, I'm not really sure what the rest of the clues here are going to look like.
yeah, I can fill them in uh, if you
Well,
like.
Halogen, so nitrogen would be... Nitrogen's a halogen. No, is nitrogen a halogen? Or is that fluorine? Fluorine's in the halogens.
So it turns out the halogen,
Fluorine,
the third halogen is bromine.
Yeah. Then
Um,
Greek letter would be... Yeah, I'm not aware of an order to the prefectures.
well, yeah, we don't have to get them all, so maybe we don't know the order of the prefectures. Uh, that's fine. We don't have to get them all.
Which president are we concerned with?
The president is well, it's either Harding or Warren Harding. We don't like that's the president, but like it's not clear. Also, like you could try H or W. Like neither of those seem to help. It turns out the relevant Summer Olympic host city is Athens. So we got to do something. So like, it turns out they are ordered. Actually, that there is a number, but like we
Are
don't
they somehow
necessarily. Maybe we didn't.
interweaved with the other drawn letters we got on the other set? I can't remember exactly which ones gave us those graphed letters.
Well, yeah. So that's the idea. Like we would, if we interweave them and we take these first letters, like A for Athens and B for bromine, we end up getting nonsense. And I'm skipping to the end as if we had solved everything else and try to read, and we end up getting nonsense for these. Like these letters don't make sense actually. But
I'm assuming we still need to
So-
answer the questions, right? Like, it's not like we
yeah,
can
we still need to answer at least most of these.
Yeah.
So yeah, so maybe. Oh, do you have an idea?
I don't.
Okay, so I'm gonna bring in another team member to think about this. So this is very common. Like we get stuck and we ask for help from someone else on the team to take a fresh set of eyes, and the fresh set of eyes says, "Did you use the number that's not a 1?"
Yeah. April, so is that like April 5th or something? Indigo 5?
Indigo 5th, the 5th of Indigo.
I don't know what that is.
What is the 5th of Indigo? I think the 5th letter in Indigo. So.
Oh. Okay.
Impressively, these not only are these mostly 1 numbers prime, and they have the lengths that match up with these Morse code messages.
Yeah, that's crazy.
Also, the number that's not a 1 picks out a relevant letter for the puzzle.
That's impressive.
So the 5th letter of April is L, and you can do the same. So the 2nd letter of bromine is R, and we do the same for like all the other ones we can solve. Let's say. Okay, so we did.
This
Twin
is
prime.
a very impressively designed puzzle.
Oh yeah. Swapped halves, I think we didn't do, right? Yeah. Okay, so here we did we did T9 and we got all these. So can we get a letter from these things? Does anyone I'm gonna kind of speed things along a little
Knight
bit.
might refer to the L shape, or the L movement pattern the knight takes in chess.
Capital of
That's a
Florida
fair
is
guess.
Tallahassee, but I don't know how to get a letter out of that. It could be, I don't know, maybe it's a T.
Yeah.
Oxygen might just be an O.
Could be.
I like that.
Perfect fourth.
So
IV maybe for perfect fourth? Like in Roman numerals? I'm thinking of like, I don't know if a fourth is a thing in music theory, but it sounds
What
like
about music?
Ring. I mean, O is a ring, but
it's true. O is a ring. So I'm gonna bring in. Let's say we have someone very experienced with puzzle hunts on our team, just to speed things along a little bit, because this is kind of like sometimes it kind of depends on that sort of thing. So, have any of you done a UK style crossword, or also known as a cryptic crossword?
that rings a bell. I think I have, but I don't. Is that like where
Okay.
like there's a downward clue that goes through the answers to all of the other puzzles?
Not necessarily, no. So the UK style crosswords, also known as cryptic crosswords, are crosswords where generally the answer is not trivia, but wordplay. And cryptic crosswords tend to come up in puzzle hunts every so often. And I will say that someone who has done cryptic crosswords, who is looking at this, will notice some of these look like cryptic crossword clues. So things like Hollywood ending and false start and capital of Florida and center of attention and Central America.
Oh,
If you view them through the lens that this is a wordplay clue.
Is Central America like the center of the word America or something? Like Eric or something like that? Or
it is the center letter of America. R. Hollywood ending is the ending letter of Hollywood.
Yeah.
What is the head of steam?
S, I guess.
It's start.
False
start.
start.
The start
is F.
False. It's F. It's the start of false.
Presumably the center. Or center of sweet.
Yes. And the center of attention, I think, is N.
Yeah.
The capital of Florida is very funny because Florida is written capitalized. Oxygen is just O. Ring is also just O.
Okay.
I don't really get why the other answers are what they are, but I have them. But this is most of them.
Knight is indeed F.
Okay. I think knight is N. It's the notation, algebraic notation for knight.
Yeah.
I think that's what it is. But
Can I see the answer for perfect fourth? Because I'm curious what they put for that.
It's F. F is a perfect fourth above C, and it is also the first
fourth letter of perfect.
Yeah, you're right. That's the reason. It's the fourth letter of perfect. Yes. And hit as H, because it's the start. I don't know. It turns out that'd be that. Okay. Yeah, so this doesn't spell anything, but the reason it doesn't spell anything is because I filtered to halves. So let me skip to having done all the stuff.
Right.
So if we've done all the stuff, we have L chair and Charlie and C, R, O, Lima, Delta, Houses of Parliament was Houses of Parent. CRT happened to be crochet. You can do that by cross-referencing the NATO alphabet or whatever.
Gotcha.
So we can get that, and then you look up all the Bond films and you see the order and you pick the right letter out of it and you get a T, etc. There's some Warren and Harding both have A as its second letter, so it doesn't matter.
Oh, cool.
The W is the five W's, and whether you think the relevant one is where or when, E is the third letter either way. Oakland Raiders and Raiders, the second letter is A regardless. Yamagata is the relevant prefecture. Um, and we already said the letters, and the drawn letters we already had. You put those all together, and we get this message. And I'm going to go back so we can actually read it horizontally. Back to the other share. Oh, whoops! I didn't mean to stop the share, but I'll fix it in a second. Here's the here's the window. I think it's visible now. And okay, so all those letters that we, and in practice we won't have all of them. We'll still be confused about a few, but we'll have most of them. But most of them is enough to figure out the whole message. We get this.
The factors of none of the factors of n
n.
only differ in their first and last digits.
Yeah. So that n at the top of the page, that is the product of 240 digits of primes. 140 digits primes. We have the hint now. The factors of n only differ in their first and last digits.
We can take the square root and trial division.
I don't think that's here because
that doesn't work. Yeah, so it's not
doesn't?
that simple. No, because if they differ in their first digit, the square root is way off from both of them.
I think if you just like look at the middle bit, you should probably get a bunch of information about what the numbers are.
Well, I think we
But I
can do a
don't think-
similar trick to just reading back from the right side, similar to the the
Yeah.
one with the like twos and like the 1 2 3 like the low high pattern. Because like each time we're only picking one of 10 letters to move from the right to the left. With the exception of the last digit, because then you have two options, but like then you should just be able to read right to left and then pick like just have like sort of a branching strategy.
That might work, but because all digits are possible instead of the convenient restriction of 1 2 3 7 8 9,
Yeah, it might be a little bit more.
I think that probably doesn't work. Or maybe it does, but that's like harder than intended. I'm not sure. I haven't tested that.
I mean, I guess.
But I worry that.
Sorry. I guess we could do like another. Maybe there's a similar algebraic approach that we could do, similar to what Cyberpunk 2007 said, where we like say b times x plus like y times b times, or rather 10. I guess 10x plus y versus 10x plus z, and then add.
Well, okay, hold on a minute. There are only if we look at if we consider the pair basically of the first and last digits of each, it's like we have only 1,000 different combinations essentially at most, right?
How are you getting 1,000?
Just for, well, no, not, it's actually less than 1,000. It's way less than 1,000 actually, because they have to be distinct. Like the two pairs at least of them.
Oh, I see. The first and last digits of the first, and the first and last digits of the second. Okay, so
yeah.
First and last digits, like 1,000 possibilities. Let's just call it 1,000.
Mm-hmm.
What do you want to do with those though? Because we don't know the other digits. I'm not sure what you intend to do.
Yeah, I think it might have went off in a bad direction here actually already. Let's
that's fine.
Let's put that on the back burner for now.
Sure. So, yeah.
Like, I think the right quarter. No, I don't know what I'm thinking. Like the right quarter, the number would have to be sort of vaguely resembling a perfect square, because like it would, like if we're just truncating, like we can imagine. Let's just name these numbers. Like we're saying the factors of n differ in their first and last digits. I just want to be able to talk about them. So let's just call them p and q, and we'll say that p is like a. Yeah, sweet. We'll say like p starts with like the digit a and ends with c, and then everything in between is b. And like we can do the same for q. Like q is like, Z then B then or like Y then X then B then Y. We'll say.
Can we do like R, S, and T?
Sure, that's fine.
R,
Um,
S, T.
except S is B, so like
S is B? Oh, right. I'm sorry, yeah. R,
Right.
B, T.
How many?
Sure.
I feel like I should know how many digits B should be approximately, right? It should be like 100 and should be like 68 digits,
yeah,
right?
yep. Mm, Wait, so
So no,
what
P
you?
and Q have 140 digits each. We're told that.
Oh, right. So B is 138 digits.
Yeah, there are 138 digits in between the R and digit and the
Oh,
T
my
digit.
bad.
But so like,
Yeah,
yeah,
I introduced a factor too.
so now like if we just imagine like B concatenated with T and B concatenated with C and we like square it, we should be able to, or sorry, multiply those two things, we should get the like the last quarter of the number. So I'm imagining if we just truncate off the last quarter of the number and then factor that, then we can.
I don't think I think N is too large.
Yeah.
Uh, I
Um,
I think what you're saying is true, but N is too large for that strategy to work
Wait, but
without
it's
if you don't
effectively
ask
the
it.
same approach as twin primes. We just square root it. Like we square root the last quarter. It should be fast, right?
No, yeah, you find some of it the number, right?
But that tells us
Wait,
that tells us the whole number except for
We
R
can
and A.
take 10 square roots, actually, one for each like like for the most significant digit, just go through like 1 through 9, or actually so 9 square roots, and then we can just like basically look at all of them for like we can look at their modulus 10. Basically, we can search a bunch of low digit numbers, right? Mod
Wait,
10.
I don't even think you
hmm.
need to do that. I think it's simpler. Like if we say the last quarter of n, so like the last 70 or yeah, the last 70 digits of n, like the square root of that, uh, if we don't have a weird carrying situation, um, then if we like square root that, then that should give us like uh,
So
just
when
modifying the
R
digits. Yep.
multiplies,
Sorry.
when R and A multiply by the B's, don't they mess that up or no? Maybe not.
Uh, oh shoot, they do.
Or I guess there's only 10. There's only 100 possible. Well, we could kind of account for 100 possibilities, which I think was what Cyberpunk was saying. So, huh?
Yeah, I guess that would be
Maybe
possible.
maybe this does. Uh, this is interesting. This might work. I have not pre-tried this, and this a new idea, so I'm trying to think on the fly. Um, so I guess in saying that, I'm implicitly revealing I have a method which is maybe more straightforward or more direct, I guess is the word I would use. Um,
Okay. Um,
but maybe this will work. I just have to like if you write up the algebra later and see if it works, that would be cool. I can't do this in my head, but it sounds maybe plausible. So one thing I'll say as an idea that's still kind of similar vein to the swapped halves idea is P and Q are mostly the same. They have like these B digits in the middle. And so my idea, let's say one of your teammates has, is consider the difference. What could we say about the difference?
it should be like
Mostly 0 in the middle.
yeah.
Yeah, so this is going to
Or it could
be,
be mostly 9 in the middle.
P is less than
or
Q,
it could be
so
mostly not.
it should be all zeros.
That's true, but either way, it definitely equals like this for like small x and y. That's for sure. Um, and so like I said what I said. I said P and Q, so
Yeah, no,
take Q minus P.
the ones digit of Q could be greater than the ones digit of P, so it might be a minus Y,
Yeah,
but yeah,
that's true. And so, y, at least without even giving any thought, y is between like -9 and 9,
Yep.
and x is between like like 1 and 9. And you can give it a little thought and like cut off like X actually can't be 9 and Y can't be odd, but like who cares about those things? So this gives us possibilities for the difference. Not many possibilities at all. So if we had the difference, what could we do? What could we do with that?
We can find another equation, maybe.
What's another equation?
I'm
Like so we have one
Just like-
equation Q minus.
Like, are we just gonna be doing like? No, I don't know. Hold on.
What's another equation that we know of P and Q that's on the screen?
N equals PQ.
Yeah, N equals PQ, which we could write as like P times P plus Q minus P, for instance. So we can solve for P with the quadratic formula.
Oh, cool.
So we have what, like 9 times like 19 or something, you know, like 1,000 cases or 100 cases, whatever, or 300 or whatever arithmetic says.
You can test
But
it.
in
It's
each of
fast
those,
enough.
yeah, in each of those cases, it's fast enough. And so, okay, so that's great. So we do that, or we do two swaps idea if it works, and we find the factors. And remember, the puzzle said the factors of n, like read appropriately, will tell you the answer to the puzzle. So these, these are the factors. And they differ only in the first and last digits. That's true. What do we do with this?
Well, it looks like
How do we read?
the middle part seems to be where the information's encoded, and once again, that looks like letters.
Yeah,
Yeah.
same cipher.
So the middle part, we just take out the first and last letters. Obviously, we're sort of garbage, and then the rest we can read. And when we read it as letters, we get this. Sorry. We get more than this because it's so long. Sorry, we get that.
Eurozone. Okay.
So what does this say? Just so people.
Well done. The
clear?
answer you're looking for is Eurozone. The rest of this number is filler.
Yes. And if you type in Eurozone into the answer box, it says you're correct and you solve the puzzle.
Cool.
So the answer was Eurozone, and the rest of the number was filler. And there are 240-digit primes that, except for the first and last digit, encode, this very long message.
Yeah, that's impressive.
Basic cryptography.
Yeah. And so let me go back to the puzzle before we conclude, just to sort of summarize what we did here. So it's like there, the factors of n only differ in the first and last digits. We use that. And so remember, the puzzle just had a number too big to factor, some numbers that are easier and harder to factor, and then some more numbers that are mostly too big to factor. And then we did all of that other stuff with the NATO alphabet, the at-best cipher, the old T9 texting standard for phones, the facts about like the prefectures of Japan, and the encoding of like which letter of which prefecture and which letter of which president, and graphing coordinates based on the factors. All of that just from these numbers. Very carefully chosen numbers in a very carefully chosen order.
Very cool.
And the answer is Eurozone. So not every puzzle hunt puzzle is all the same. They're not all this long. They're not all this complicated in terms of math or programming or trivia, but they will have some of those, and they'll almost always have multiple layers like this one did. Like we did some factoring to learn about the categories, then we use the categories to get instructions, and we use the instructions to get more little puzzles, and then we solve the puzzles to get more letters, and those were more instruction. Like that's typical of a puzzle hunt puzzle. And so if you like these, I encourage you to join you can sign up for the MIT Mystery Hunt and participate remotely. And if you don't know anyone who's doing it, you can sign up to be joined with other people who are also looking for a team, or a team that's looking for random people to join on. You can do Puzzle Pint at bars in at least the US. I'm not sure which other countries might have that. But yeah, it's fun, and I hope this example was interesting and gave you a sense for what's out there. Happy to take questions or anything.
I'm surprised at how organically we did manage to get a few of the like right track things. Of course, like it's impossible to say like without the guidance of having the pre-cooked solutions, like what we would have been able to get. But I am a little bit surprised at like how many correct steps we were able to take, even so.
Yeah. Because a puzzle hunt typically has a lot of puzzles, and you'll have multiple people on your team to look at it. So this, it was a little abbreviated because we skipped like writing the code or whatever. But, this is, a group of people together. Someone will have the next idea, often.
That was really fun.
Yeah, it was.
I'm glad.
I kind of want to. Maybe we should. Would you guys be interested in just doing another one, but that we don't know the answer to up front, just to try it out?
Yeah, I mean, we can all just fucking freaking be a puzzle team.
So, I mean, there are two different things you could do. So, if you're looking for some kind of some other puzzles to get a sense of things, there is here. This website has some examples and some discussion. Post in the chat here.
Send that. Did you send that resource earlier about with just like tables of like ciphers? Did I hallucinate that whole thing, or like different like example ciphers that are used in, or is there any resource like that that just is a compendium of like ciphers you might encounter in these puzzles? Yes, here we go.
Yeah, resources for beginners. Yeah. So yeah, there are a number of websites. So this resource for beginners has a lot of good introductory stuff. And yeah. So I think maybe, do you want to stop the recording
Sure.
at this point?